Welcome to Lecture 27. This is where we do the Fundamental Theorem of Calculus Part 2. We've already done the Fundamental Theorem of Calculus Part 1, and we're going to build on that now to get the second part of the Fundamental Theorem, which is what most people who take calculus will remember. But here's what Part 1 said, and we'll need this, and it's important. We'll do some exercises on this in a few minutes. But Part 1 told us that if we make an area function out of the integral, that is, the integral from a out to a variable x of some function f of t dt, f being continuous, then the rate of change of that area function turns out to be just how tall, or what the y value is of the function that you're integrating at the variable point of integration, that is, where the area is calculated up to. So what that means graphically is that if you're looking at the total area from some place, which doesn't really matter, up to a variable point, then how fast that total area changes is exactly equal to the y value. So the bigger the y value, the faster the area changes. The smaller the y value, the slower the area changes, which is kind of like a duh statement if you think about it, right? Anyway, this is the Fundamental Theorem of Calculus Part 1. Part 2 says that if you can find an antiderivative, that is, if capital F happens to be an antiderivative, which would mean its derivative is little f, then you can calculate the integral from a to b of this function little f simply by taking your antiderivative and plugging in the upper limit of integration, taking the antiderivative and plugging in the lower limit of integration, and subtracting. And that gives you the answer. It's a very practical result. It hinges on, of course, being able to come up with this antiderivative. Plus, we saw in class that there are infinitely many antiderivatives, and that's going to lead to a slight problem for us here, but we can deal with it. Okay, so first of all, there's an observation that we already know one antiderivative. It's not a nice one, but this function, a, capital A, the area function, this is what this is, an area function, because we've made a function out of calculating the area. So it's a variable amount, okay? But the area function itself is an antiderivative for little f because of this result, the Fundamental Theorem of Calculus Part 1, that says that the derivative of this area function is little f. Okay, now before we can go on, I've got this problem of what about other antiderivatives? Is it possible that some other antiderivative, if I plugged it in here, would give you a different answer? And I need to prove a certain little claim here. And my claim is this, that if you have any two antiderivatives, if f prime, let's write it this way, if f prime of x and g prime of x both give you little f, that means they're both antiderivatives, then actually capital F and g of x are equal to each other almost. Almost. One of them is equal to the other plus a constant, where c is a constant. Now, I didn't quantify this well. This is if the derivatives are equal for all x on the interval that you're looking at. In this case, it would be the interval from a to, well, let's make b out here somewhere, just so that x is in the interval from a to b. So as long as the derivatives, that is, the antiderivatives, work for all x, then one is equal to a constant plus the other. Okay, and to prove this, I'm going to start by looking at what happens if I subtract these two functions. So I'm going to make this function capital D, which is going to be the difference between capital F and capital G. Now D has an interesting property. What's the derivative of D? Well, clearly because the derivative of a difference is the difference of the derivatives, you take the derivative of f and subtract the derivative of g. Derivatives. And each of these guys is equal to little f. So you got little f here, so the answer is 0. So the derivative of this function that I made by subtracting these two is 0. And this would be true for all x in the interval from a to b. Now here's the thing. If I have a function whose derivative is always 0, what can I say about that function? Well, I have another claim here, which I have to prove. I haven't proved this outer one yet, but I'm getting there. The claim now is that d itself is really a constant for some constant c. All right, so again, what I'm doing is I know that the derivative of d is 0 for all x because I'm assuming that f and g, capital F, capital G, are antiderivatives, so they both give me f when I take their derivative. So if I make the new function capital D out of the difference, then the derivative of capital D is going to be 0. And my claim is that therefore d as a function is really a constant function. Now how do we know that? Well, here's where we do this proof by contradiction that we've done before when we were playing with things with the mean value theorem and solving equations. I'm going to assume that this is not true. In other words, suppose not. Suppose that d is not a constant function, so that would mean then d would have different y values somewhere. So let's pick two places where d has different y values. So let x1 and x2 be places where d has different y values. So that would mean d of x1 and d of x2 are not equal. Okay? So again, what we're doing is we're supposing that d is not a constant function. I'm actually going to prove that it is by contradiction. Something's going to go wrong here in a minute. But suppose that d is not a constant function. Then d would have to be different at different places somewhere. So there's an x1 and an x2 where the y values, applying the function d to these two things, would give you different answers. So here's a picture. So you've got an x1 somewhere. Doesn't matter which one's bigger or which one's smaller. Just got two different values for x, and the d values are just different. Okay? I don't care which one's bigger either. Then what is this number? You've all seen this before. D of x2 minus d of x1 divided by x2 minus x1. This, of course, is the average rate of change in going from x1 to x2. And that's also the slope of this line. But see, d of x1 and d of x2 are not the same number. So that numerator is not 0. So this fraction is not 0. Okay, but this is the average rate of change. And the function d obviously has a derivative, because it's the difference of two functions that have derivatives. And the mean value theorem tells us that the average rate of change must be equal to the instantaneous rate of change somewhere. So somewhere between x1 and x2, there's this value where the derivative at this value, let's call this point P, all right? Somewhere, the derivative at point P has to be this average rate of change. This average rate of change, which is not 0. But wait a minute, there's something wrong with this picture. You know what's wrong? D, remember d was this function whose derivative is equal to 0 for all x in the interval. And here we found a point where the derivative is not 0 because The average rate of change is not 0 because we assumed that there were two different y values for this d function. And see, that's a problem. You can't have two different y values for a differentiable function whose derivative is 0 everywhere, because the mean value theorem says somewhere you're going to have an instantaneous rate of change of 0, but you're assuming that there is no place where the instantaneous rate of change is 0. So this is hopeless. This is a contradiction. So something went wrong, and what went wrong was the assumption here that d took on different y values. So d cannot take on different y values. So d really is a constant function. So the difference between these two is a constant. And what are these two? These two are antiderivatives. So what I've claimed is that if you have two functions that have the same derivative, then they really are equal to each other up to a constant. So one is equal to the other plus a constant. Well, go back up here a minute and see what we have. We have capital F, whose derivative is little f. But we also know that the area function, remember the area function, a? A is a function whose derivative is little f, where a is this ugly thing, right? A prime of x is equal to little f. So, my question is, what if you had another antiderivative for little f, like capital F? And I'm not even caring what capital F is. If capital F is any other antiderivative, we've just shown that capital F and capital A are really the same thing up to a constant. So I'll write that down here. So capital F is really equal to capital A plus some constant. Now, the fundamental theorem of calculus here that I'm trying to prove is that this integral from a to b of f of x dx is capital F of b minus capital F of a. Why don't we just try and calculate and see what that is? What's capital F of b minus capital F of a? Now don't blink. This is going to go real fast, and it's going to look like magic. Well, just substitute. What's capital F? We know that it's capital A plus a constant. So that would be capital A of b plus a constant minus capital A at A plus a constant, right? Take another look at that. Capital F evaluated at B means, using this formula, you could take capital A and evaluate it at B plus a constant. And then this is capital F at A, so that means you replace x by A, and that gives you this. And of course, when you simplify that, the c's cancel. They never mattered in the first place. And you're left with A of B minus A of A. Now, remember what A of x was? A of x is the integral from A to x of f of t dt. So what is A of b? A of b is just replace x by b. It's the integral from a to b of f of t dt. Minus A of a, well, that's the integral from a to a of f of t dt. Oops, you've seen this before. The integral from a to a of anything is going to be 0. So you're left with just the integral from a to b of f of t dt. And that's it. Because the integral, well, I had x here, but remember xt, it's a dummy variable here. That's not going to come into the answer. These are constants on the top and bottom, so this is a number, an area. So the integral from a to b of f of t dt, f of x dx, doesn't matter, is equal to capital F of b minus capital F of a. That's it. That does it. And that is the fundamental theorem of calculus part 2. All right, let's look at a few problems. And one of the problems that you need to be able to do is to calculate easy derivatives, and these are really, really easy. So what would the derivative of the integral from -4 to x of the square root of t squared plus 1 dt be equal to? Well, what are you dealing with? You're taking the derivative of an integral which has a variable on top. Well, this is an area function. It's just like what you see immediately above it, where the role of a is played by -4, and the role of f of t is played by this function. And the answer to the derivative of an area function is the function you're integrating evaluated at that number. So you get the square root of x squared plus 1. It's this function evaluated at x. Does it matter that it was -4? Absolutely not. The change in the area depends only on the last value, the x that's here. It does not matter where you started. So the answer to this is square root of x squared plus 1. Okay, let's try another problem. This time this is a little different. What would the derivative of, let's try the same problem, except I'm going to switch the limits of integration. Now, this is not exactly the same as what you had up here, but I can make it equal to that simply by going the derivative of the integral from -4 to x of the square root of t squared plus 1 dt, except that's not quite true unless I put a minus in front here. Okay, so the derivative of this integral is the same as the derivative of the same integral with the limits switched, as long as I put a minus here. And now I can just read off the answer from up above, because this is the derivative of an area function. That minus doesn't do anything. It's just going to sit there and watch while I take the derivative of what's inside there. And so the answer is simply minus the square root of x squared plus 1. So that's pretty easy. All right, let's do one that is going to be a bit more complicated, but you get used to this very quickly. Let's suppose we want to take the derivative of, and actually I want to pick a particular problem here. I want to do the derivative of the integral from 1 to e to the x, the derivative of the integral from 1 to e to the x of log t dt. All right, now I want you all who are watching this to know that this particular problem will be on the quiz on Friday. So pay attention, because you can just remember how it goes and just write it down. This will be one of the problems on the quiz for sure. In fact, it may be the only one, but we'll see. There may be one other one. The derivative of this thing, how do we think about this? This is not x, but I want to take the derivative of something that looks like an area function. Now wait a minute, is this really an area function? Well, let's see, the area function would have looked like this, wouldn't it? The integral from 1 to x of ln of t dt. This is an area function, and I know that the derivative of that would be ln of x. But this isn't the same thing. This is not x here, this is e to the x. But wait, isn't this the same kind of thing as we've done before with the chain rule? I mean, after all, isn't this thing that I'm taking the derivative of, it's not a of x exactly, but isn't this really a of e to the x? I mean, look, if you go to a to the x and replace x by e to the x, isn't that what we're dealing with in this problem? It's the integral from 1 to e to the x. The rest of the stuff's the same. So really, it's the area function, but not at x, at e to the x. How do I take the derivative of a of e to the x? Well, the chain rule tells me how to do that. I take the derivative of the outer function, But instead of plugging in x, I plug in whatever's there, namely e to the x. And then the chain rule says you got to multiply by the derivative of what's inside. But what's a prime at anything? Well, a prime at x is just the function you're integrating. So a prime at e to the x would mean, in this case, natural log of e to the x, which actually reduces because log and e to the x cancel. So this part of it just turns into x, and then you've got an e to the x. So from here, you can say that that's just equal to x e to the x. So that's the derivative of this horrible mess. Okay, one more time, because this is on the quiz for sure. Guaranteed. This problem is on the quiz for Friday. So what happened? We're taking the derivative of something that looks like an area function, but it's more complicated because up here, instead of having x, we have e to the x. All right? And that's just like saying we're dealing not with the area function at x, but we're dealing with the area function where you replace x by e to the x. Look and see that these two things are exactly the same, except for the upper limit of integration is not x. So how do we think of that? It's the derivative, not of a of x, not of the area function at x, but the derivative of the area function at e to the x. And this is a chain rule problem. So the derivative of a function is the derivative of the outer function, plugging in whatever's there, times the derivative of what's inside. Okay, the derivative of the area function is just the integrand, the thing that you are integrating, the function in here, evaluated at x. But this says the derivative of the area function, which is the integrand, not evaluated at x, evaluated at e to the x. So it's natural log not of x, but natural log of e to the x. And that just reduces to x. It wouldn't be fatal if you wrote natural log of e to the x here instead of x, but it would lose you a point because you really should know that natural log of e to the x is x. Natural log and the exponential function are inverses of each other when you do one on top of the other. You are taking the log of e to the x. You're not taking log and multiplying it. That doesn't make any sense. Okay, so this is the chain rule. This is a chain rule type of problem. All right, let me do one more problem of this type that's even harder. This one will not be on the quiz for tomorrow, for Friday, but keep this one in mind because this is on the quiz, okay? What if I do the integral from, let's do something weird, sine x to cosine of x of something ugly, e to the x squared, or excuse me, e to the t squared dt. Okay, now this is something you're not going to be finding antiderivatives of. Besides which, the question is not to find the antiderivative of this. You've got to calculate the derivative of this with respect to x. Well, now the problem is you got stuff on the top and the bottom that's variable, and how are we going to do this? Well, unfortunately, it's going to take us a few steps. I'm going to split this integral up into two. So we'll start from sine of x, and I need a constant. And you can pick any constant you like. It really doesn't matter. You can pick 0 if you like, and I guess I will. But you could pick anything. It really doesn't matter. Just pick a constant. Pick your favorite number. And it's the integral from sine x to 0 of e to the t squared dt plus the integral from 0 to cosine of x of e to the t squared dt. All right, so that is how you split up this integral, because the integral from a to b is the integral from a to any c plus the integral from c to b. And we've used this fact many times. So I just stop at a constant. Okay, now this has the variable on the bottom. We've been there before. I'm going to switch it. So that's the same as the derivative with respect to x of the negative of integral from 0 to sine of x e to the t squared dt plus, no, I'm distributing my derivative, the derivative of integral from 0 to cosine of x e to the t squared dt. Okay, so the minus down here isn't going to matter. And what are we dealing with in here? This is just like what we did a minute ago for that quiz problem. It's an area function with, instead of x here, we've got a sine of x. So the answer is the derivative of the area function, which is the integrand, the function you're integrating, with a minus in front because of that minus. So it's that function, except it's not evaluated at t, it's evaluated at sine of x. So it's sine of x squared, that's the exponent of e. But then the chain rule comes along and says, oh, you got to multiply by the derivative of what was inside the area function. So the derivative of that is cosine of x. Okay, now over here, the derivative of this guy, this is again the derivative of an area function, except that it's not x up there, it's a function of x. So the derivative of the area function is, of course, the integrand, e to that power squared, but that power is cosine. So it's e to the cosine squared of x, because it's cosine of x that is evaluated, that you're plugging in for t. All right, look again up here. It's the derivative at that argument, the derivative at x, that is the integrand at x. So you got to plug in this guy. So e to the cosine squared of x, but then you got to multiply by the derivative of what's inside. That came up here. See, this is what we're really doing. We're taking the derivative of the area function at, not e to the x, but cosine of x. All right, I'll do it here. The area function that we're dealing with is the integral from 0 to cosine of x, which isn't the same as x, e to the t squared dt, which is the area function, whoops, excuse me, I meant to write, the area function at cosine of x, where the area function, a of x, is the integral from 0 to x of e to the t squared dt. So you see, this area function at x gives you this, but the area function at cosine of x gives you that integral, area function at cosine of x. So the derivative of this is really the derivative of this. And the derivative of this is a function of a function governed by the chain rule, so it's going to be a prime at cosine of x times the derivative of what's inside, which is going to give you minus sine of x. So the derivative of the area function is the integrand, not evaluated at t, but evaluated at that upper limit. So that's why you're getting this e to the cosine squared of x. But then the chain rule says you're going to have to multiply by the derivative of what's inside there. So that's where this other minus sine of x comes from. Okay, the exercises will walk you through that, and we'll do these in class for sure on Friday. But you need to be able to do that one for the quiz. All right, let's do one example of the fundamental theorem of calculus, part 1, and then we'll call it quits. So how about the integral from -5 to 5 of e? That's kind of a stupid problem. Let's do one that's a little bit more complicated. The integral from 0 to pi over 4 of secant theta, tangent theta, d theta. Secant theta, tangent theta, d theta. Okay, In order to do this problem, I need an antiderivative for this function. But I've seen secant theta, tangent theta before. The question is, what do I put in the parentheses so that the derivative of what's in here is equal to secant theta, tangent theta? Because I'm looking for an antiderivative for this guy. So what do I put in here? And if I remember my derivatives, the derivative of secant theta would be secant tangent. So this is an antiderivative. So all I got to do is take this antiderivative and plug in this, take this antiderivative, plug in that, and subtract. So the answer is secant of pi over 4 minus secant of 0. Okay, and secant is 1 over the cosine. Cosine of pi over 4 minus 1 over cosine of 0. And cosine of pi over 4 is square root of 2 over 2. So the reciprocal of that is 2 over square root of 2. And cosine of 0 is 1. So that's my answer. I'm sticking to it. Okay, that's about enough for today. We will do some problems, and then when we come back from break, we will talk a lot about antiderivatives. Bye.